Oops. New stuff.
Is this like that test too?
No, not on the next one, but it'll be, haven't quite decided. I think I'll just put all the tests on Wednesday. A small chapter 4 test and then the final exam.
Next Wednesday?
Wednesday after that. Wednesday after that. Alright, so last chapter. 4-1. I want to get a last test on this one in because technically it is the easiest chapter in the whole book.
Yes, it is.
Even if you go into calculus, this stuff is the easiest topic to deal with. Exponential functions. The only trouble with exponential functions is people forget their exponential laws. For instance, laws of exponents. Like a to the n times a to the n equals what? A to the m plus n. You add the exponents. And law of 2, if you have, I'll put them out of order. It really doesn't matter, but these two are the ones that people screw up all the time. A to the m raised to the n. A to the product of their powers. Power to a power you multiply. Alright, and then a to the m divided by a to the n is equal to, subtract the exponents. For, what would be a good one? Oh, a to the negative m is equal to
1 over a.
1 over a to the n. Negative exponents are also known as reciprocal exponents. They take fractions and flip them. So if you ever see something like ab raised to a negative exponent, all that means is to take its reciprocal. So what's the reciprocal of a over b? B over a. Probably one last one that's kind of important. I mean, there's more subtle ones, but these are the main ones. A to the 0. 1. Anything raised to the 0 power is automatically equal to 1. All right, the other thing that confounds people just a little bit is when you're writing an exponential expression, like a to the n, a is called the base, n is called the exponent. But people get very confused about what the base is. I've had people ask me if this is 2x cubed, isn't the 2 also being cubed? And you have to be really careful. When you see 2x cubed, what's the only thing being cubed? The x. So the x gets called the base, in this case. The 2 is called a coefficient. It's just a number that's sitting in front of the base multiplied by it. And then, of course, the 3 is the exponent. So hopefully that alleviates weird things like this. What's negative this equal to? I shouldn't even say it in English. Because if I say it in English, you can misinterpret it. But if you write it down, it's actually kind of clear what the answer should be. That's not the answer. See, the base is the one that's touching the exponent. The negative is not touching the exponent. Just the 3 is. If I want the negative to touch the exponent, I have to write it this way. This is negative 3 times negative 3, which is 9. If I just write an x all by itself, what number is sitting in front of it? 1. Guaranteed without a doubt. What property is that? Remember the beginning of the year? Properties? I told you they'd come back to haunt you, and this is one of them. Where's that 1 come from? What property allows you to put a 1 in front of anything? It's not multiplicative identity, maybe? Multiplicative identity. So when you write negative 3 squared like this, you really have a 1 in front of the 3, and then it's being squared. That's the identity property. It allows you to put a 1 in front of any number. Well, 3 is a number, and I could put a 1 in front of it. If I do that, the 3 is the only thing being squared. So technically, the base here is 3. So what's the negative 1, or the negative in front called? technically like a coefficient. So the base is 3, it's being squared, the final answer really is -9. So you have to be really cautious with what you call a base with an exponential. You can't go too far. Most people understand that the 2 is not being cubed here, but a lot of people think the negative is being squared, but it acts just like the 2 up above. So you got to be a little cautious with these things. All right, so with those under our belt, let's discuss what makes an exponential function. F of x is equal to some base raised to the x power. Now, normally we're used to x being in the base. Here, x is representing the exponent, the power that we're raising it to, and b is some fixed number that keeps getting raised to different powers. What numbers could b? I shouldn't use b. What numbers should b not be? What numbers would be irrelevant for it to be? Out of all the real numbers that b possibly could take on, what numbers do you really not want it to be? Fraction's fine. Think of simplistic numbers. What was it? Negative causes a problem. We'll come back to that in a few seconds. That one's a little harder to talk about. 2 easy numbers. That would make it not even an exponential. 0 is one of them. So guaranteed, letting b equal 0 is useless, so we throw that out. Because 0 raised to any power is just 0, and it's not an exponential function anymore. What other number just kind of wipes out the whole idea? 1, because 1 raised to any power is also 1, and that kind of gets rid of the exponential. So we remove those 2 values right off the bat. Then we have to talk about the negatives. Why can't b be a negative? Well, it's kind of a complex answer. You willing to listen? It's not hard. You all understand the basic topics of it. So let's let b be a few numbers. Let's let b be -2. And then we're going to take -2 and raise it to the x power. Simple negative number. All right, let's choose a few negative exponents. -3. -2 to the -3. You have to go back to this law over here. If you see a negative exponent, it's on the wrong side of a fraction. So -2 to the -3 power, put it in the bottom, is the same thing as 1 over -2 to the 3rd power. What's -2 to the 3rd power? 1/8, -1/8, right? So this becomes -1/8. -2 to the -2 power. The base is -2, the power is now -2. What's -2 to the -2? +1/4. -1 power. What's -2 to the -1 power? Is it 1 or -1? -2 to the -1 power is 1 over -2 to the 1st power, which is -1/2. The negative's not going away there. So if the number is odd, the answer is negative. If the number is even, the answer is positive. So -2 to the 0. 1. -2 to the 1st. -2 raised to the 1st power. -2. -2 raised to the 2nd power. Is it -4 or +4? It's +4. -2 raised to the 3rd power. Well, -8. It's -2 times -2 times -2. One problem with choosing a negative as a base is, notice just between the integers, the numbers are just going back and forth between positive and negative. All right? What if we choose something weirder? What if I choose a half? What's -2 to the 1/2 power? What's a 1/2 power also known as? Square. Put the other word with it. Square. Oot.
I said that.
I heard square.
I just thought, what are you talking
Where I
No.
Yeah, you whisper people. So this becomes the square root of -2. What's wrong with that?
Can't square that.
So what's the answer? I squares of 2. The problem with this is it's not even a real number, so I can't even plot it. So right off the bat, that function now becomes discontinuous at that point. There's a hole in my graph. If I choose 1/3, is there any problem with that? Well, no, that's the cube root of -2. I don't know what its answer is, but it's a real number. But then I get to 1/4, and I get a 4th root of -2. What's wrong with that? That'll also generate a I. 5th root will generate a number. 6th root will generate an I. So anything with an even in the bottom is going to generate a bunch of I's. So for these two reasons, B cannot also be negative. B cannot be negative. And B cannot be, well, B has to be, positive. Let's get rid of 0 there. B is strictly positive. So this is a weird interval that it works on. It starts at 0, stops at 1, starts at 1, and goes off to infinity. So B is one of these type numbers. So it's a little strange. Can't be 0, so it has to start just to the right of 0. Then it has to stop at 1 again, jump over 1, and then it goes 1 to infinity. All right. So we're going to talk about this in two pieces. That part and this part. The 0 to 1 part and the 1 to infinity part, they behave just a little bit differently. But you could always force, for the most part, part 2s to look like part 1s. There's a way of forcing it over, but we'll talk about that later. Alright, so let's talk about what the function looks like if it's in the 1 to infinity range. B is bigger than 1. These are the easier ones to deal with. So for example, and they generally have this same form, if I take a simple exponential, 2 to the x is actually the easiest of them, and try to find what it looks like, then 3 to the x, 4 to the x, 5 to the x, they generally have the same shape. It's like a base function. Alright, so if I try to graph this, can we do it in our heads or should I do a table? Let's do a table, be safe. Here's what x is going to equal. I don't know why I wrote it like that over there. I'm confused. And over here, 2 to the x. 2 to the x. Of course, we should start in the negative, so how far back do you want to go? I'd go one more, but if you want to just do -2, that's fine. -2. 2 to the -2. Is it 1/4? Yeah, 1/4. -1. 2 to the -1. -1/2 or just 1/2? Remember, negative exponents just means it's on the wrong side. So 2 to the -1 is the same thing as 1/2, which is just a half. 0. 2 to the 0. 1. Nice, easy one. 2 to the 1, of course, is 2. 2 to the 2 is 4. Just for fun, if I plug in -3, 2 to the -3 is what? 1/8. Now, one thing to notice is, no matter what value of x you plug in here, the answer is always going to be positive. It is never going to be negative, because the base isn't negative. The power can't make it negative. So this graph, or whatever's happening here, has to remain positive. All right, so let's do a little sketch of it. 1, 2, 3, 1, 2, 3, 3. So notice all my graph is on the positive side of the x-axis. So if I plot -2 1/4, that's right here. -3 1/8 would be half the distance, to the x-axis. -1 1/2, right about there. 0 1 1 2 2 4. So you get something that looks like that. It takes a little bit more work to get the curve to smoothly go between these 2 points. Remember when I talked about graphing a long time ago, that a lot of weird behavior can happen between points. But I'll tell you right now, this is a very nice, smooth, continuous graph. So obviously this thing looks like it's going to keep on growing rather quickly. This part of the graph is called exponential growth. It is growing with exponential ferocity. Interest income, population growth, things like that. This side, if we turned it around and face it to the right, this is called exponential decay. How far down is it going to go?
0.
Will it ever get there, though? Because it's kind of like a half of a half of a half of a half. You're always going to have a little bit left over. So what does that make the x-axis in this case? Which kind? It's definitely not vertical because it's not pointing that way. So it better be called, this part of the graph, just the left-hand side, is the horizontal asymptote. So even an exponential function has an asymptote. It's not exactly like the rational function, which is an asymptote in both directions. This is just an asymptote in the negative infinity direction. So that's the graph of 2 to the x. And anything that has the base bigger than 1 is going to look something like this. Does that make sense? It's not that hard. Domain? Range?
On that side too.
What do you mean, what is that? That has nothing to do with it. What's the range? How low does it go? Yes, you can. What's the lowest possible value it can obtain? 0, and it goes off to infinity. You got to be careful how you write it, though. Domain is negative infinity to infinity. The range is 0 to infinity. What has to go here? Bracket? Does it ever get to 0?
No.
No, so it's got to be parentheses. So that's its domain and range. Never touches the x-axis, but it starts a little bit above it. All right, while we're talking about base graphs, what if I want to graph this? Back to transformation of graphs. Did we talk about this the other day? Yeah, we did. When we were talking about the rational functions moving around, this is the same thing. What does the 4 do? What's it do? Is that mumbling? I was hoping to hear it clearly. It goes up 4. You said that. I just wasn't
No, I
sure.
really didn't.
You did? No. What's the 3 do? The 3? It's close.
Is that the point? I don't know.
Well, it's the close one to the x. Which way does it move the graph? Up and down is determined away from the x.
Right?
Is it right?
Yeah.
Left? Which one?
Oh, left is opposite.
Opposite direction is left, so this is left 3. And what's the negative do? Over.
It, line.
Well, you were going to say horizontal, right? Yeah, it flips over the horizontal. you're going to do it in order, you should flip it first and then translate it, but I do mine all at one time. All right, so you sketch a little graph. You know this thing is going to go up 4 units. So you put it in a horizontal line at y equals 4. You know it's going to go left 3, so you put in a vertical line of x equals -3. And then you have to depend on what does the original graph kind of look like. Well, it has a horizontal asymptote that hugs the x-axis. When it gets to the origin, it intersects one up from it, one high from it. So you have to hug the x-axis from the negative side. You have to move up 1 and plot a point for the origin point, and then it just grows exponentially. The only thing that's going to screw that up is it's being flipped over the horizontal. So instead of, I should draw a little bit more on this side. Instead of hugging the top of the horizontal, this graph is going to hug, it's getting flipped over the horizontal. So instead of hugging the top, it's going to hug the bottom. So it's going to hug the bottom until it gets to the origin point. Now the origin is here, but the graph doesn't go through the origin. It goes one high. But if it gets flipped, it's going to go through one low. So it's going to go through this point. What's the coordinate of that point? Now think about this. It's 4 up, 3 to the left are my 2 reference axes, and I want to go down 1.
3.
So what's the coordinate of that point?
-3, 3.
-3, 3. Alright, so the graph is going to hug the x-axis on the bottom, go through this point, and then exponentially grow down. So you get a graph that looks something like that. So the graph was shifted up 4 units, left 3 units, and flipped. Does that make sense? It's a little weird looking, and you just have to kind of get used to the picture. All right, what about this graph? Since we don't know what it looks like, we should plot a table, construct a table, and then we can plot some points. What numbers do you want to pick?
-3.
Yeah, might as well start there. You pick -3. What is 1/2 raised? Let me write it. 1/2 raised to the -3 power. Number 1, what's the negative due to the fraction? It flips it. It's a reciprocal power. So then that becomes 2 to the +3, better known as 8. If I plug in -2 for x, that becomes 1/2 raised to the -2. But the negative again flips the fraction, and it becomes 2 to the 2nd, which is 4. Plug in -1. What's 1/2 to the -1 then? What is it? I whispered class. 0 is 1. 1 1/2 raised to the first power. 1/2. 1/2 raised to the second power. 1/4. 1/2 raised to the third power. 1/8. Notice the numbers here and the original graphs that we did over here. We started with 1/8, 1/4, 1/2, 1, 2, 4, right? And then 8, if we wanted to go there. But this is completely backwards. It's been flipped. So what is the graph flipping over?
Horizontal. No. Vertical.
Vertical. It's actually graphing backwards. This graph, instead of having the hugging the negative x-axis, it hugs the positive x-axis. Still goes through 0, 1, and goes off to infinity in that direction. So this is the type 2. This is the part 2 I was talking about. For numbers that are in the interval 0 to 1, your base is on that interval 0 to 1, that's its base graph. This is technically the decay function. Radioactive decay. It decays over a period of time and becomes less and less radioactive, I guess you can call it, or radioactive material. Like U-238 changes into lead, which is kind of cool. So any piece of lead that you've ever touched is slightly radioactive.
Yeah.
And that's why they use it for x-rays, because it's already got the radiation pounded out of it. It doesn't absorb very well. Okay, so what's another way of writing this g of x? Well, it looks like it was just flipped over the y-axis. And one way of flipping over the y-axis is to take the x variable and multiply it by -1. Huh. So let's think of it this way. If this is a half to the x, can I write it as 2 raised to some power? In other words, take the 2 out of the bottom, bring it to the top. What happens to the exponent? It's negative, so it becomes -1 raised to the x, which is the same thing as 2 raised to the -x. So because the negative is on the x, it flips over the y-axis, so you get this graph. So either way you want to think about it. If you want to think of it as a half of x is going to decrease over its entire domain, that's fine. If you want to take the 1/2 and change it to 2 to the -x, that just tells you to take your graph and flip it over the y-axis. So this first graph is technically the exponential growth graph. This one is called the exponential decay graph because it's always coming downhill, always decreasing. All right, break time for a little bit? I'll torture you some more after. This in 8th grade. Should have learned this in 8th grade. I might be right, I might be wrong. So this is the compound interest formula. It pretty much says if you take a chunk of money, you put it into a savings account, and you let it sit there for a certain period of time without touching it. The big important part is without touching it, no more deposits, no more withdrawals. Then this formula will tell you how much money you're going to have in the future based on all the interest that you earn. Now the good thing about this interest is it has an exponential factor to it, so that means it looks kind of like those graphs that we were drawing for exponential growth. If you let it sit in there long enough, it will grow huge. There was a story I read in one of my math books that some guy lent George Washington, good old President George Washington way back in 1774, $200,000 in gold. I think it was about $200,000. And the government never paid him back his gold. So his family, I think it was 20 years ago, sued the government for that money. And they did a calculation based on this formula, and it came out to $12 billion.
Did I get it?
No, but they got about $12 million out of it. But with compound interest, even if you kept the interest rate really small, the amount of money that the government owed these people after 220 years was astronomical. The government could never do it. It was ridiculous. They should have paid them back a long time ago. So this formula does generate a lot of money over a lot of years. Okay, so let's say we let P be $1,200. Let the interest rate be somewhat high, 3%. And N means how many times you compute interest per year. It's called compounded monthly, compounded daily, compounded annually. So if you say compounded monthly, which is most banks' savings accounts, you get a statement every month saying how much interest you earned, then N would equal what? If it's compounded every month. Yeah, so how many times per year? 12. So then in this case, let N equal 12. And let's let it sit in there for 25 years. So this just represents compounded monthly. If it was annually, then that's the other famous one, annually. Annual interest rates are usually inflation. How much our money either degrades or upgrades over time. When the economy was really bad, our money actually became worth, was it less or more? I think it's less. and as the economy gets better, our money is worth more. It's a little weird. During the bad economy, a lot of product prices either stayed flat or went down. And now they're starting to go back up. If you haven't bought hamburger lately, the price of hamburger or beef has gone way up. Okay, so plug everything into the formula and you get A equals 1,200 deposit plus, make sure you write 3% correctly. What's 3% as a decimal? 0.03. If you write 0.3, that's 30%. So 0.03 divided by the compounded monthly. That gets copied down twice because n is in both locations, down in a fraction, up in the exponent. And then t, of course, is 25. Now you need your calculator to do this, and I highly suggest you do one calculation before you do anything else. Which one do you think you should do first?
Bottom of the bracket.
Nope. The exponent. That's where a lot of things get tricky. If you type this into your calculator, the answer to this is 12. What you're trying to do over here is raise it to a product. To do that, you have to put it in parentheses. So most people forget to put parentheses, so I highly suggest you do 12 times 25 first. 12 times 25 is 400? 300. 300? 300. So this is equal to 300. And then the fancy calculators, you can just type it in exactly the way it looks. 1,200 parentheses, 1 plus 0.03 divided by 12 parentheses, caret for the exponent, 300. What you get?
25, 38,
32. So this is how much money is in the account after 25 years.
I'm trusting on calculation.
Why
I
not?
can't use calculator.
What is with people talking with their hands in front of
I can't use a calculator, right?
Did anybody else get this answer?
I don't-
Okay, we're going to trust her, please. She messed up last time.
Yes,
Come
we're
on.
going to trust her.
Y'all have to learn how to do this because I'll have things like this on the test, and if you calculate it wrong, I mark it wrong. What is it?
Yeah,
That's right. So if you started with $1,200 and you ended up with $2,500, what's the difference in these numbers? What's that called? I mean, the amount of money that they paid you is called interest. So any difference between these two numbers is how much the bank paid you for the use of your money, which is a good thing rather than the amount you pay the bank for the use of their money. That's bad interest because it costs you money. But of course, the two percentage rates on those two are completely different. They're going to charge you a higher percentage rate when they give you a lower one. And there's a reason for that. Does anybody know why?
They are my money.
If you want their money, you're going to pay for it. Number two, people default on loans, so they have to kind of cover that with a high percentage rate. A lot of defaults lately. Well, in the past 5 years. All right, another one is what's called continuous compounding. Now, continuous compounding works on this little feature. Do you remember LIM? What's it stand for? Limit. So this is basically saying let x get really, really big. As big as you want it. If I write this, it has a specific answer. If you type this into your calculator and let x equal 10, x equal 100, x equal 1,000, what happens is you get close to a very specific number. And that value, let me find out what the value is, 2.7128 something, something, something. Let's see. 2.718281828. And it goes on forever and ever. So as you make x larger and larger, you get closer and closer to this value. I think I put in x as 1,000,000 one time, and I got the first 4 decimal places, which isn't too bad. So as you get bigger and bigger with x, you will start approaching this number. This is like pi. Pi 3.14, blah, 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 goes off forever and never, ever stops. What kind of number is pi? Irrational, right? cannot be represented as a fraction. This is another one that's called irrational. This number we're going to represent with e. So we don't have to write out 2.718281828. E is just a fancy number. It's called the natural number. It's called the natural number. It has a lot of neat features. If I take the compound interest formula and I say let n go off to infinity, basically compounding every second of every day for an entire year, actually every millisecond, then this formula turns into this formula. A equals PERT, where RT is an exponent. I can show you the derivation of that, but most people get lost during it. Just trust me. If n goes off to infinity in the compound interest formula, it turns into this formula. Because if you look at the 1 plus 1 over x raised to the x, the compound interest formula looks somewhat similar to that. So there's, some basis to this argument. So this one's kind of cool. This one calculates what would happen if your growth was continuous. Now, certain things grow continuously. Populations, bacteria growth. Weird thing about bacteria is if you let it grow for 10 years, if it didn't die off or have things kill it, we'd be swimming in bacteria on this planet because it grows so fast. Thank God it gets killed pretty easily too. So this formula is kind of cool. If you want to calculate out pretty much the same thing with a continuous compounding, you start off with $1,200. Your interest rate is 3%, and we did it for 25 years. To get the E on your calculator, you have to type in the 1,200. You don't have a calculator. You have to hit second ln. ln is on the left-hand side of the calculator, as I told you to buy. Yours is on the left-hand side too. Second ln. And then type in 0.03 times 25.
Parentheses or number point.
You don't need to. With this, it gives you the parentheses automatically. Yeah, that sounds about right. 2540. So this turns out to be 2540. And some change. So you get a few more dollars. It's not a lot, but you get a few more dollars out of the deal. But this formula better describes bacteria growth, radiation decay, anything that has to do with continuous growth or continuous decay. So that's called the A-PERT, or continuous compounding formula. And then that E number becomes really important for the next sections. All right. So that's all.